Okay, let's take a look at our wave video here that we just recorded. And let's see what happens. Okay, so have a look here. And they'll come one more time. Eventually. There it goes. Okay. Alright, so what I did was I took a little screen cap of that, and we're just gonna take a second and examine, what's going on here. So the spring here is going to be known as the medium, okay? So the medium has kind of a resting position, which you would see as, just that spring stretched out in its normal sort of form, okay? And the wave comes as a disturbance in the medium, all right? Or this type of wave does anyway. So if we look, the medium is disturbed in that direction. Got a little bit clearer. In this direction here, okay? What we would call this is a wave pulse, okay? So when we have essentially like a single disturbance through that medium, okay, that travels along, we call that a wave pulse. Now, these have some names, okay? So, oops, just don't lose it like that. Switch back to here, okay? So we call this the resting, or if you want, null position of our medium, okay? We would call this probably a crest, and if it were a full wavelength, we'll talk about that in a minute, we might see this, and we might consider this a trough. That's sort of up for perspective, but if, say, you were to have a wave that looked like this, okay, you were to draw it from the side, this would most likely be called your crest and your trough. Just because that's sort of, the way you would view it in terms of like water waves, right? Okay, so about this thing. The entire length of the disturbance we call a wavelength. Okay? In this sense, as a pulse, actually, since there is only one, I guess, hump moving along, in this case, we could consider that to be the wavelength, but in general, a wave looks like this. It's the full crest plus trough. And so the wavelength is from the start to the finish of the wave, okay? If we were to extend this into what's called a wave train, in other words, there's a whole bunch of waves coming along, you can also measure your wavelength from crest to crest or from trough to trough, and they will always be the same length. Does that make sense? Okay, now there's a symbol for wavelength. It looks like this. And that symbol is called a lambda. I always, for some reason, forget that one, but it's called a lambda. Okay? So this symbol right here is a lambda, and that represents the wavelength. Okay. So what else can we say about this? If you measure from the resting position, which in this case is the dotted line or the null position, to the height of a crest, or to the depth of a trough, okay? So this value here from resting to crest is called amplitude. We call that A or amplitude. So amplitude is equal to rest, crest, or to trough, okay? Oftentimes, people will mistake and think that the amplitude is from a crest to a trough. That is incorrect, okay? It is only from resting position to the height of a crest or to a trough. Okay, the direction that a wave is traveling in, along with its speed, is called the velocity. The velocity of the wave, okay? That is measured in meters per second, and it will have a direction attached to it, okay? So it's essentially how fast it's covering ground, if you want. So in this case, this guy was moving this way, it then reflected and moved back, but we would draw its velocity, say up in this direction here, okay? There's V for velocity, that's the way it's traveling. Okay, so some things to note. Once the wave has passed, as it has over here, okay, so this wave has already gone by in this direction, you notice that the medium returns to its null position, okay? So in other words, there is no transfer of medium when a wave goes by. It's a disturbance in the medium. In fact, it's a transfer of energy through the medium. The medium itself is not changed really in any way, right? Once the disturbance passes, it just returns to normal. So we should write that down. Waves do not transmit the medium from one place to another. Okay? So what the wave is considered to be is a transfer of energy. So a wave is a transfer of energy from one place to another. Okay? And again, no medium is moved in the process. When you think of water waves, right? The waves come up onto shore, and yeah, some water will come higher up onto the shore, but it always rolls back into the ocean, right? If there was a net transfer of water via waves up onto the shore, eventually, you know, you'd end up with all your water up on the shore, which clearly does not happen, okay? So a wave is just a transfer of energy or a disturbance in the medium as the wave goes by. The magnitude, or the size, if you want, the size of the velocity, the magnitude of velocity, or if you want how fast it's going, of the wave, depends only on the medium. So, in other words, this wave here, okay, when we pulled this tighter, we noticed that the wave went faster, okay? So when there was more tension in the spring, that caused the wave to go faster. If you play any instruments, you might kind of have an understanding of this, that when you tighten a string on a guitar or whatever stringed instruments you play, the pitch will go up, okay? That's because the waves are traveling at different speeds through the string. And there's a little bit more to it than that, but that's the basic principle. As the medium changes, the velocity of the wave changes. It will not matter if you were to say, like, do this in, you know, a different level of gravity, say, or you were to do it vertically or horizontally. The only thing that affects the speed is the nature of the medium itself. If I switched to a completely different medium, like a much heavier spring or something like that, I would find that the velocity of the wave would slow down in a heavier spring or speed up in a lighter spring, and so on. Waves in water travel at the same speed for the same depth and temperature and type of water, but if you change to shallower water, or you change the temperature of the water, or possibly even if you change the density of the water by, say, adding salt, you would change the velocity that the waves travel. So it's just based on the medium itself that dictates the velocity of the waves. Okay, so have a look at this now. This is a slightly different type of wave than the one we've just seen, a little harder to see. But you notice it traveling along here. Have another look. Another one will come here in a second. Oh, we missed it. Let's try again. So there it goes, okay? Did you guys see that? Okay, a little bit tough to see, but I'll pull that into our little movie so I can draw on it. Okay, so here's a little shot from that video, and what we're sort of looking at right here is this little bit of a blurred out section. So if you look up here, what you noticed is that the medium is disturbed, if you want, perpendicularly to the direction that the wave is traveling, right? So we've got the velocity in this direction, but the disturbance in this direction. Okay, so we say that the velocity and the disturbance, or the displacement of the medium, are perpendicular to each other. This type of wave has a name. It's called a transverse wave. Transverse. So if you want, this is your transverse wave here. In the name, I mean, transverse means across, or, at a right angle to. This type of wave is where you are compressing the spring, right, in this direction, and then releasing it. So essentially what you have is you have an area of the spring that is compressed. It's a little harder to represent this, but if you think of these dots as being the resting, scenario of this spring, what you'll find is just before this disturbance, you have a stretching out. Okay, so you have a wider position, and then you have a compressing area here. Okay, and then quite possibly a stretching out, and then back to normal resting length. Okay, so in this scenario, your wavelength is the compression and the expansion, or if you want, rarefaction. Okay, so this is called a longitudinal wave. I've got to find colors that work on here. Longitudinal. And in it, the medium is displaced parallel to the direction that the wave is traveling. So the velocity is this way, but the individual particles, as the wave passes, move in this direction. Okay? So instead of having like this kind of a shape, you now sort of have, you have to kind of draw it as if you want, little dots that are representing what we're trying to talk about here. It's a little bit tough to kind of show this, but that's kind of the idea, that there's a compression area and there is a rarefied, or a rarefaction area. Okay? And then the wavelength is that sort of combination. So there's your wavelength. Okay? Okay, so longitudinal wave, and this is velocity is parallel to displacement. Okay, so also amplitude in this case, right, is a little bit hard to define. Doesn't necessarily really apply in the same sense that it does for a longitudinal wave. However, if you have a larger rarefaction than this, and a tighter compression, we would say the amplitude is larger. If we have, less of a compression and less of a rarefaction, we would say the amplitude is smaller. But to directly physically measure it in this picture is quite difficult to do. Okay, does that make sense? Okay, so that's the basic covering of waves. And these, by the way, are considered mechanical waves. So these are the two types of mechanical waves that we've covered. Okay, and mechanical just means they take place in a physical medium. And so, like, some things that exhibit waves, or that are waves, would be, waves in water, maybe waves in air, which we often call sound, if they're within our range of hearing. Even waves in, like, say, a tabletop, or anything really that you, say, smash with your fist, that vibrates afterwards. Okay, so all of these have a source of energy. Like, for instance, if you splash water in the bathtub, right, from that source, you'll get your water waves traveling outward from it. If you whip a skipping rope, right, you get that sort of a thing going on. And if you talk, right, with your mouth, you are actually compressing and expanding the air kind of outward from your mouth. All right. So sound is longitudinal. wave in a skipping rope or a spring like we saw. Transverse. And a water wave kind of has, it's sort of transverse, but you have this like rolling action. We'll look at a few animations in the future just to clarify that a bit more.